Hello, friends. I'm Dr. Sonali Tamankar presenting the AI A to Z course. Today we have AI for the builder, F is for foundation models. I guess it's only appropriate that this course is also building. We did E is for embeddings yesterday, and tomorrow we'll discuss the transformer architecture that is used by most foundation models. In G is for GPT or generative pre-trained transformer. If you didn't watch E yet, I've got you. We'll make today self contained. In traditional machine learning, we typically have one model, one task kind of thinking, what might be called narrow AI. We might have an ED visit predictor that only predicts the risk that a patient has a healthcare emergency. If we have a new problem, like predicting diabetic complications risk, we must build a new model. It's like having a totally different tool for each problem. This narrow approach feels wasteful, right? Can't we use knowledge gained from one problem into some kind of an advantage to solve another? Enter foundation models, a foundation on which you can construct different kinds of structures. It's like having a Swiss knife, high quality Swiss knife. Let's talk today about how the foundation models are built and how we can use them for different applications. So, to build a strong foundation, we need a lot of data. Where does this data come from? Everywhere. Crawling the internet, books, other proprietary data, whatever the builders can get their hands on. Even after we have a ton of data, this is not labeled. So, like in C is for clustering, we are in a situation where the model must learn from the data itself. How? The brilliant solution is to use self-supervision. Just ask the model to predict the next word based on all the words it already saw. So, if you provide the text, Winnie the Pooh reached into a jar of, and ask the model to predict the next word. We don't label the data labels itself. Yesterday in E's for embeddings, we saw that words are converted into numbers. So the model is doing a whole bunch of math. You reward it if it gets the answer right and keep training it on mountains of data for a long time. This brings us to questions of energy used during training, questions of access, because only the biggest companies have the infrastructure and the finances to do this. The training data also may have only certain languages and cultures represented. There are copyright issues when the training data is used without the creator's permission or even knowledge. This is a nuanced topic. But let's say we have thrown all this data and energy and money at the model and trained this foundation model that is now doing a good job at getting the next word right. Okay, now remember, these are generic models where the topic can be anything. It can be a recipe, it can be Shakespeare, general theory of relativity, a Python code, Taylor Swift. To do a good job predicting the next word on all of this training data, the model has to compress the information somehow. A foundation model has billions of parameters, sometimes millions even, but it's trained on trillions of tokens. So it can't memorize the internet verbatim, right? It's too big. So to compress it, it has to learn the patterns and logic behind the words. It learns the grammar, the humor, the reasoning. It learns that water is wet, so to say, just so it can predict what comes next efficiently. So that's what your chatbots are doing at the core. They're just predicting the next word and the next word till they generate an end token and you have your answer. Okay, now there are different kinds of foundation models. In addition to familiar language models, there are also vision models, DNA models, EHR or electronic health record models with their corresponding training data. But the idea is the same. Do a one-time heavy lift and then apply it to many use cases with slight modifications, as if our Swiss knife had modules that we could swap out. So, for example, some of the parameters of a generic healthcare foundation models can be slightly adjusted using specialized training data to solve one specific problem better, like healthcare emergency risk or diabetic complications risk. This is called fine tuning. The point is, because our foundation model is doing the heavy lift, this final piece can be thin. It doesn't take as much computing power to tweak the foundation model once it's built. Modern foundation models are heavyweights. They have read pretty much every book and seen every medical journals. So when you swap on this diabetic attachment, for example, it doesn't look just at the numbers like A1C. It understands the context, making the tool infinitely smarter than the old toolbox. There are other kinds of custom layers like prompt tuning, and we'll cover P is for prompt engineering and R is for RAG or retrieval augmented generation later. We'll also talk about LLMs or large language models specifically. There's lots of fun stuff ahead of us. And I'm so glad that we are using these beginning alphabet topics to give us a strong foundation. Foundation models in biology have mapped out the shapes of almost every protein on Earth, over 200 million of them. This helps scientists develop new therapies for diseases like cancer in months instead of years, and might even help us breed stronger honeybees. The 2024 Chemistry Nobel Prize went to the creators of the foundation model AlphaFold. So this illustrates the power of these models. This extends far beyond generating cute poems. They have become a fundamental instrument in scientific discovery. So what do we take away today? Foundation models are highly successful and a huge investment. There are billions of parameters, distill knowledge from many sources. They pretty much read the whole internet. And finally, further tweaks can be applied for specific applications. So thank you for going on this 26 windows into AI tour with me. What questions or comments do you have so far? We'll meet again tomorrow to talk about GPT or generative pre-trained transformer. Have a nice day.